Mm. Yeah. No. Is everything good? Okay. I'll move this thing. Okay, I think it's time to get started. So we have 2 more lectures left, today and tomorrow. Hopefully that's a good thing. The summer is beginning. So in these 2 lectures, I want to cover 2 major concepts. Well, we're going to finish prefetching today. This will be, let's say, relatively easy and more researchy also, so you can relax a little bit. And then we're going to cover the fundamentals of virtual memory, which is going to be much more fundamental, let's say. I mean, prefetching is very fundamental. The reason we're covering it is it's so important in today's systems. But I'm going to give you some, let's say, advances in prefetching that can have very quick impact on real life, let's say, because these things, if you actually find a way of improving prefetchers in systems, you can relatively easily get it incorporated, assuming you have a good idea in real systems today, because memory latency is such a big deal today. And tomorrow we'll continue with virtual memory, and then we will probably talk a little bit more about like what comes next in computer architecture. Does that sound good? Okay, I see some nodding. That's good. Okay, so hopefully you remember there's an extra assignment. I'm going to give you another one in the beginning of the virtual memory lecture. And this is easy to do, so I encourage people to do it. It's good for people to have read Amdahl's seminal paper. Not many people do that. There's a difference between knowing something and knowing of something, right? Richard Feynman is very famous for making this very clear. You can know of Amdahl's paper, or you can know Amdahl's paper. The way to know it is by reading. Knowing of it, you already know of it. It's already here. Right, okay. Okay, so readings, these are the same. So we were covering prefetching, and we covered actually many interesting things in prefetching. You can right now innovate in this area potentially, but what, when, where, and how are important questions. And we covered some of the things on the slide. Clearly, we didn't go into a whole lot of detail in everything, but this is just to jog your memory. So I'm going to give you, we actually covered some prefetchers like stride prefetchers, stream prefetchers, etc. I'm going to give you some more examples of prefetching today. And again, you can relax over here because this is, I'm not going to ask you questions on this one, on the exam, for example. But I wanted to give you like what's happening today. What are people thinking about? And I think this is a very interesting direction in systems today. How do you actually optimize the system by designing components that can learn, that can become better over time? So we call this self-optimizing. And this is a work that one of my PhD students did. You can actually read the paper. You can download the code and play with it. Many people have done that. I'm going to give you the idea. And the idea is using reinforcement learning to enable the prefetcher to make decisions by itself as opposed to somebody dictating those decisions. How many people know about reinforcement learning? Okay. How many people do not know about reinforcement learning? It's also fine. Where did you cover reinforcement learning? You just learned about it yourself? Yes. Mathematics. Okay, so you learned about mathematics. So this is an area that could be covered in mathematics, in computer science, and also in psychology. The first place where I covered reinforcement learning was in psychology, because the roots of reinforcement learning are in psychology. How many people know about Pavlov's dogs? Okay, Pavlov's dogs, right? These are dogs that Pavlov, who was a famous psychologist, who trained these dogs such that whenever he rang the bell, he gave food to these dogs. So over time, this person rang the bell, and even if he didn't give food, the dogs were opening their mouths basically to get the food. That's reinforcement basically. You, in a given state is ringing or not ringing of the bell. You associate a reward. With the ringing of the bell, you give food. So the dog knows that he or she is going to get food every time the bell is rung. And after some time, whenever the bell is rung, the dog is opening their mouth, right? So that's basic reinforcement learning, essentially. Essentially, all of us are reinforcement learning agents, human beings. That's a very, very important form of learning. It's not the only form of learning. Some people claim that it's the only form of learning, but I don't believe that that's the case. But essentially, we're all reinforcement learning agents, right? When I actually go to a stove and I touch my hand on the stove, if it's hot, then I learn that I'm not going to do that again. So that I get a negative reinforcement, essentially, or negative reward if the stove is hot. So I learn to associate the hot state of the stove with a negative reinforcement. And in the future, I learn not to repeat that. So essentially, machines can be built to operate based on these principles as well, right? Essentially, reinforcement learning in its general computer science terminology, it's an algorithmic approach to learn or to enable an agent to learn to take an action given a situation to maximize a numerical reward. And there are clearly a lot of things that can go into action, situation, and reward. Situation is called state in computer science in general. But basically, you have an agent interacting with its environment. Agent observes the state, the situation, essentially. And then agent decides to take an action based on the state. And it gets a reward immediately or delayed. So it can be instant or delayed over time. Essentially, over time, it figures out what action it should take in what state so that it maximizes the reward, right? It makes sense, hopefully, right? That's what the dog was doing, right? It was opening its mouth so that it quickly gets the food. In fact, Skinner, who was another famous psychologist, he was the first person that is at least documented to teach pigeons, these are called Skinner's pigeons, to deliver notes in World War II to specific places. Using basic reinforcement learning principles, he was able to do that essentially. So essentially, if the pigeons can do it, why not the machines, right? That's the idea. Not to say, not to think low of pigeons. I think pigeons are actually quite smart, but machines can be also designed by humans to do the same thing, right? So essentially, there are multiple forms of reinforcement learning. In one form, agents store some intermediate values called Q values. This is called Q learning. For every state action pair, of course, every state action pair is hard to represent, so you need to actually coarsen the granularity of representation to enable storing of the Q value so that you can generalize as well. And then this Q value specifies the expected return for taking a given action in a given state, essentially. And given a state, the agent selects the action that provides the highest Q value. So if you have multiple actions to choose, you observe, for example, it's raining outside, and you decide whether or not you take the umbrella. You think about the reward internally, and the reward of taking the umbrella is probably larger, has a larger Q value, right? Essentially, that action has a larger Q value. Okay, so basically, you can formulate prefetching as a reinforcement learning problem as well. I will give you a higher level overview. I don't want to go into a lot of details because details matter when you actually create a reinforcement learning agent. Essentially, the agent is the prefetcher in this case, and the environment is the processor and the memory subsystem. It could be the workload as well, more broadly. State is what you observe from this environment. Essentially, it could be the features of a memory request to address A, for example. It could be the program counter that you observe. It could be some other state that you observe. And action you take could be to prefetch from some offset. And the offset may be determined. Basically, different actions may lead to different offsets are essentially different actions, right? And then you get a reward based on your selection of the offset. And then your goal is to really maximize some long-term reward. In prefetching, it's a long-term reward because you're looking at the long-term performance of the system by selecting the best offsets based on the states. And internally, you update your table so that you actually hopefully get the right offsets. Makes sense, right? Of course, if you really want to learn how to do this, you need to figure out how the mathematics operate, which is not the purpose of this course. But I'll give you how you set up the problem. Essentially, you need to set up the problem to specify the state. What does the designer do, basically? Designer doesn't say, oh, I'm trying to detect a stride, for example. Designer doesn't say any of that. Designer says, here's the state for you to observe, agent. And let's take a look at the state. State can be a k-dimensional vector of features. And features are now the subject of creativity. Basically, you can come up with many, many features, control flow, data flow. In this work, for example, we basically fed program counter, the branch program counter, last 3 program counters. These are different control flow features, right, that the processor has executed. It could be the branch history register that gives you an idea of the state where you are in the program. Data flow examples could be the address that you've touched recently, multiple different addresses that you've touched recently. What is the physical page number that you have touched? We're going to talk about virtual memory. So physical page number is essentially a chunk of memory that you're touched, which memory region you're operating in. Delta between 2 consecutive cache line addresses. We've seen that before, right? We talked about deltas. This is essentially stride. But you can also have multiple deltas, last 4 deltas, last n deltas. So all of this could be part of the observation state of the agent. And the agent hopefully tries to make sense out of the state, basically associate these state action pairs with Q values. So what is action then? This is important to, again, specify because action could be something else. But in this work, the specification is that given a demand access to address A, initiated by a load or store, the action is to select prefetch offset O, or multiple prefetch offsets O1, O2, O3, at O4, etc. You can also learn how many to prefetch as well, right? So by setting up the problem right, you can actually do different things. And action space is limited over here because of what we will discuss later, virtual memory size, the page size. So basically you have 127 different actions, 127 different offsets we consider. You can actually consider more. We limited it here. And a 0 offset in this case means no prefetch is generated. Sometimes you don't want to generate a prefetch because you get whatever offset you choose, you get not so good rewards, right? Basically, it may not help your performance. Okay, so you can actually prune this using design space exploration as well, both the state as well as the actions. And then the reward is actually one of the most important things in reinforcement learning. And this really defines the objective of Pythia. This is essentially the prefetcher that we named. Essentially, in the reward, you need to encapsulate multiple metrics, right? Is your prefetch useful? And how much damage is it doing? Like, is your prefetch accurate? Is it late? It is out of the page that you're accessing right now. This will become more clear when we talk about virtual memory. And what is the status of the system like? Is there a lot of memory bandwidth usage that's happening? Is there cache pollution that's happening? Is energy problem? Basically, you can incorporate these different things as part of the reward function. And you can read the paper for more detail, but this is essentially the configuration that's derived through automatic design space exploration. This is the state, this is the action, these are the rewards. Don't worry if you don't make sense out of this, but basically these are the reward values that you update your Q values with, assuming your prefetch is accurate and timely, for example. Reward value for a prefetch that's accurate and timely happens to be a very large reward. But you also get a negative reward if you actually, for example, causing cache pollution and late. Okay, so you need to set up the problem so that the prefetcher is able to learn. And I believe we're all reinforcement learning very kind of set up that way, but maybe not as rigidly as this is done over here, right? Maybe we're much more flexible and we evolve also, right? Somehow. So it's good to look at the analogies and contrasts as well. So just to give you an idea of how this sort of prefetcher behaves, it's very different from what we have discussed so far. There's a Q value store, which is multiple tables essentially. it records these Q values for all state action pairs. So given a state, you index this table, and then for multiple different potential actions that you can take, you get the Q values. And you pick the action with the highest Q value or highest N Q values, right? So you pick multiple actions potentially. Right? So this is essentially in the steady state, hopefully this tells you what action you should take under what state. And again, this design of this is important because this table can be huge if your state space is huge. And also action space is usually smaller than the state space. State space can explode significantly. So you need to design your table such that essentially you can generalize. So generalization is also important in learning, in machine learning. If you cannot generalize from a condition, then you have to learn every single state, right? But if you can generalize the general state and what you should do in a general state, you don't have to learn every single possible incarnation of a larger state space. Okay, so there's an evaluation queue. This is essentially recently taken actions. But basically, when you get a demand request, you assign a reward to the corresponding evaluation queue entry. And you generate a state vector over here. And you look up the QE store over here, Q value store. And this Q value store essentially gives you multiple different potential actions you can take. Essentially, these are different offsets. Given this address A, what offset should I prefetch? And each offset essentially has a Q value associated with it. And you pick the action with the maximum Q value. That's hopefully this agent has been trained such that that action is going to be the most useful for your reward function in the long term. And then you generate the prefetch with that offset. If that offset is 0, you don't generate a prefetch. That gets sent to the memory hierarchy. And then the prefetch action and state action pair is set into the evaluation queue. This is where you evaluate what happened to the prefetch. And at some point, after the evaluation queue evicts this entry, you update the Q value store. So essentially, if while the prefetch is in the evaluation queue, prefetch completes, you set the fill bit, and you actually update whether the prefetch has been useful, what the state has been, etc., and you update the Q values. Again, for more detail, you really need to see the paper and understand how reinforcement learning works, which is not the function of this course. This is basically showing that reinforcement learning can be applied to this problem if you actually set up the problem right. You need domain expertise, of course, to set up the problem right? If you don't know about prefetching, you're not going to be able to set up this problem right. You may know about reinforcement learning, but if you don't have the domain expertise, you cannot set up this problem. Okay, so essentially, if you do this, in the end, the results look quite good. The prefetcher, don't worry about the numbers, etc. over here. This is not an industry slide, as you can see. This is a real research academic slide that shows that the performance of Pythia is better than state-of-the-art prefetchers, some of which are similar to what we have discussed earlier. Okay, and then also this is actually a very bandwidth frugal prefetcher when you don't have a lot of bandwidth in some systems, for example, you don't have memory bandwidth. It's still much better than prior prefetchers. In systems with little bandwidth, sometimes people turn off the prefetchers. If you're in a data center setting, for example, they say, oh, I'm running these workloads that are very bandwidth intensive. I don't know what the prefetcher will do, so I'm going to turn off the prefetcher. Right? That's what a lot of people do, actually, because they cannot guess what will happen. You can also see that some of these prefetchers actually degrade performance in bandwidth limited settings, which is true. So this prefetcher actually doesn't, as you can see. But if your bandwidth is ample, you still improve performance. Okay. Okay, so if you're interested, you can actually experiment with these things. This is completely open source. It's artifact evaluated, as you can see. And you can learn more about it, actually, in Rahul's video. Rahul is my PhD student, and in the paper as well. But I wanted to give this out to you also because this is really important to think about going into the future. And I think in general, a lot of the things that we have discussed in this course can potentially be automated in this fashion, right? Caching mechanisms, for example. You can also consider caching mechanisms as a reinforcement learning problem. Of course, you need to fit the problem or modify the problem such that it fits reinforcement learning principles a little bit. Memory controllers, which we did not discuss much, but it's essentially we did some work in 2007, 2006 that essentially formulates the memory controller problem as a reinforcement learning problem. And if you're interested in reinforcement learning, I would recommend, I should have put that book over here. I'll put it in the revised version of the slides. There's a beautiful book by Sutton and Bartow that essentially covers lots of stuff on reinforcement learning. It's all free. You can find the PDF online. If you search for Sutton and Bartow, Sutton has done a lot of work on reinforcement learning. You'll find that book. Okay. Okay, any questions? Now let's go back to reality a little bit. Well, these prefetchers may come up downstream later in the future, who knows, right? For example, we talked about the perceptron branch predictor. When it was written as a paper, it was not implemented immediately. About 10 years down the road, it was implemented in processors, right? We have perceptron branch predictors in some processors today. These are the people who have actually written papers about it. Some people implement these things and they don't write papers about it, so you don't know what some of these processors do, but they may actually have perceptron branch predictors. Who knows, maybe we'll have reinforcement learning based mechanisms inside processors also in the future. But real systems actually have hybrid hardware prefetchers because patterns are not easy you have multiple different access patterns. If you remember the slide that I showed you last week, where I asked about predictability, right? These are different access patterns actually. And multiple prefetchers are used to cover many access patterns today. This leads to better prefetch coverage in today's systems and potentially better timeliness also because you're specializing the prefetcher to the access pattern nicely. Unfortunately, this is more complex. There are many design and optimization decisions in such prefetchers. Bandwidth intensiveness becomes even a bigger problem if you have many prefetchers, essentially sending requests to the memory system. And prefetchers also interfere with each other. So this causes contention and pollution. So you need to manage accesses from each prefetcher in a nice way. So essentially, designing hybrid or multiple hardware prefetchers is not easy also because you need to manage them. So that management problem, again, could be a reinforcement learning problem or some can be done with machine learning in a better way. Let me also talk about, we covered this caching in multi-core, right? Caching becomes more important in multi-core because memory bandwidth is precious, etc. That's all true for prefetching also. Essentially, if you want to be more aggressive in the memory system and prefetch aggressively, you should be a lot more careful in a multi-core scenario where you have lots of processors or threads accessing memory. So for example, prefetching efficiency is a lot more important. And the interference of cores requests, for example, one core's prefetches can interfere with another core's requests, demand requests as well as prefetches, right? And then there is also the prefetching shared data problem, right? We have discussed sharing data between multiple processors, and you may have coherence misses because somebody invalidated the shared data block that you were supposed to read. Now, how do you prefetch that? That's an interesting issue, right? Again, I'm not going to give you answers over here, but I want to point out that these issues are much more pressing and important. Yeah, I think we already talked about a lot of these, so I'm not going to talk about this in detail, but you do need to throttle prefetchers. And prefetch throttling is actually an important area as well. Existing systems all throttle prefetchers. The question is, how do you do it? Again, I won't bore you with a lot of details, but you can read a lot of papers. Actually, we have done a lot of work in this area. That's why I'm going to flash you a bunch of papers. But this is actually evaluated by IBM also in their some of their works showing that these techniques actually work in their systems as well. So I will just skip these because we don't have time. But I will cover another class of prefetchers. I think it's important to cover because this is going to become even more important going into the future. And that's execution-based prefetching. Now, this is going to be a totally different form of prefetching. We're not going to detect patterns over here. And the idea is, I already gave you the idea basically in an earlier lecture, but you design a special program or specialized thread to solely prefetch data. Or in other words, you pre-execute a piece of your program that's pruned to prefetch data. The whole purpose of this program or thread is to prefetch data for another program or another thread. Makes sense, right? Sounds great because if you can do this early enough, accurately enough, you can actually get rid of all of the misses potentially, right? Because program does some things. Some of it is memory accesses, some of it is some other things, computation. If you can actually take out the piece of the program that does memory accesses and execute it early, hopefully you'll get the data early. So basically, you only need to distill code that lead to cache misses. So we call this a speculative thread. Speculative thread essentially is a pre-executed program piece can be considered a thread, essentially. But its purpose is not to execute the program. Its purpose is to prefetch data for the actual program that's finishing instructions. You can consider this as speculation, right? What we have seen. You're not going to retire the instructions here to the architectural state, I should say. So a speculative thread can be executed in many different ways. It could be executed in a separate processor or core. So your program is executing here, the speculative thread is executing here, it's prefetching data into the shared cache, right? Or it could be executed in a separate hardware context. Both of the threads, speculative thread and your main program are executing in the same processor, they're fine-grained multi-threaded, for example, right? As we have seen multiple times, fine-grained multi-threading. Or you could execute the speculative thread on the same thread context. You have the main program executing. When it gets to a long latency access, you switch in the speculative thread and speculative thread prefetches. I'm going to show you an example of this, which essentially we have developed in my PhD thesis, which is fun. That's why I'm going to talk about it, but it's also implemented in real systems as well. So there's a huge design space here, which we're not going to cover clearly. And then there's also the question, who constructs a speculative thread, right? As a programmer, you can do it, actually. You can do that. Not so hard once you know what you're doing. Compiler can do it. Operating system can do it for prefetching from the SSD into the memory, for example. And also hardware can do it. So we're going to see an example of hardware doing it in a cheap way, but that's not the only way of doing it in hardware either. Does this sound exciting? Okay, so you can see that this is actually a huge design space. Plus, this could be more powerful than some of the other prefetchers, right? Here, you don't need to detect patterns. You execute the program, and the program generates the address for you. Of course, it may have limitations as well. So I like this picture over here. This picture is more general than what we have talked about. So this is called thread-based pre-execution. Some people call it assisted execution. There are other names also, as you can see. But this picture shows two important things. Branches are costly in a processor, and load misses are costly in a processor. And this picture shows that, now let's ignore the branches for now. Let's look at this load miss over here. This is the main program that you're executing. And at some point, you fork a speculative program, speculative thread, that executes a piece of this main program such that it reaches this load much earlier and generates the address and handles the cache miss. And when the actual main program reaches the same load, the cache miss is already serviced and the block is in the cache and this load hits. This way, you've eliminated this latency of the cache miss, which could be much larger than that's shown over here, right? I think that's a beautiful picture that shows nice. It's borrowed from this last paper over here, which essentially developed some methods to do this efficiently. You can also do this for branch mispredictions, right? This is actually a much more general idea than prefetching. You can prefetch branch predictions, if you will. You can think of it that way. But essentially, you can construct a speculative thread that executes just the piece of the program that computes the branch condition and tests that branch condition, basically generates a prediction for the branch that's going to be executed by the main program, hopefully later. This way, hopefully that prediction is very accurate because you executed the program nicely, or piece of the program that leads to the branch, and this branch will not be mispredicted. Makes sense, right? So that's the idea. So this is a very general method to, let's say, overcome the downsides of performance degrading instructions in general. And this is one of the reasons why we have two lectures that are called advanced in this class. We talk about advanced branch prediction, which was somewhat advanced, and we talked about advanced prefetching, right? These are the two major problems, control flow and data problems that we're having essentially in systems today. So let me give you an example of this execution-based prefetcher. We're going to essentially do this, but in a, let's say, cheap way. We're not going to heavily fork something, although we're going to fork something, but we're not going to make it burdensome on the programmer or the compiler. The hardware is going to do all of this on the left side over here. Okay, so let me motivate this because I want to give you the full picture of why we did this. Essentially, remember out-of-order execution, lecture, I think 15 or 14, I don't know, one of those. We talked about out-of-order execution. We said that the size of the instruction window is important. And if your instruction window is small, you cannot decode instructions, right? As a result, you get a lot of stall. So let's look at an example where we have only an 8-entry instruction window. So you have the oldest instruction. Let's take a look at what's happening. You have a load that misses the cache. It takes hundreds of cycles. And then you have a branch that's dependent on it. And then everything else is independent. Assume that the branch is predicted correctly. Okay, so at this point, your window is full. Load is stalling the machine because you cannot retire it. Remember the precise exceptions lecture. So these 6 instructions are independent of the long latency cache miss. They're executed out of program order because of out-of-order execution, but they cannot be retired because of precise exceptions requirement, right? If you retire them, you're violating the ISA, and the programmer will go crazy, and they will never buy your machine again, right? Well, they will probably figure out that this will happen, and they will not buy your machine to begin with, right? Okay, so basically the issue is if you have a small instruction window like this, younger instructions cannot be executed because there's no space in the instruction window. You cannot even decode them. So this interesting instruction, that's a load, which will happen to be a cache miss, cannot go into the window. As a result, next time you execute this load, you get a cache miss, basically. So the processor stalls until this cache miss is serviced. And then this long latency cache miss are responsible for most full window stalls because you cannot service this cache miss while this cache miss is going on. Remember the memory level parallelism that we discussed? Now we're putting together many concepts, right? If you had one more space in your instruction window, you could have put this load and executed it. And if it were a cache miss, you would have parallelized those two cache misses, right? Okay, so we did a lot of studies with Intel, and I think I mentioned this in one earlier lecture. We actually analyzed a lot of their workloads on a state-of-the-art processor, and with a 128 entry window at the time. We're talking about 2002 right now, 2001 actually. We found out that most of the time the processor is waiting, stalling. So you can see that only 30% of the time it's not stalling. This doesn't mean that it's actually doing some useful work. It may actually, some of the screen time is spent on branch mispredictions, for example. Okay, so and most of these stalls are actually due to long latency cache misses. So with simulation as a computer architect, you can imagine, you can say, okay, what if I had a 1024 entry window? Well, in this case, 2048. You can also do 2048. Today, we're not at 2048 yet. We're large, but not that large. Maybe we're 1000, I don't know. People don't really reveal their window sizes, but again, you can reverse engineer. But basically, if you actually have a 2048 entry window, performance improves significantly. As you can see, this is average across 150 applications, 147, as you can see. So the stall time of that actually reduces significantly. Still, you're stalling a lot on L2 misses, but not that bad, right? So the goal is to actually have this large window. That was our goal when we actually designed this. But of course, I don't want to pay the cost of this huge window, right? People actually came to build larger windows over, I don't know, 15 years of research over time. And we're still not at 2048 today. So there's still more things to do. Essentially, out-of-order execution, as we have seen, requires large instruction windows to tolerate today's main memory latencies. Today's main memory latency is on the order of 500 cycles plus. As main memory latency increases, your problem actually becomes worse. Your instruction window size should also increase to fully tolerate the latency. And building a large instruction window is not easy, as we have discussed in out-of-order execution lectures, because you have the tag matching logic, you have the load store buffers, and this is actually very bad for energy. You want short cycle time. So wake up, select, register file, bypass latencies, they all actually hurt your cycle time. Or you add more cycles, pipeline more heavily, they hurt your IPC if you do that, right? Instructions per cycle, if you remember. And then if you want to have low design and verification complexity, you don't want to have any window, ideally, right? So basically, we don't want these large windows. So the technique we developed was called Runahead execution. It's essentially a technique to obtain the prefetching or memory level parallelism benefits of a large instruction window without building that large instruction window. And it's essentially a pre-execution based prefetching technique. Let me give you how that pre-execution works. Essentially, when the oldest instruction in the machine is a long latency cache miss, you can easily detect that, right? Because you know all of that information at the processor. The processor checkpoints the architectural state, which is the register file, and enters a speculative processing mode, Runahead mode. Now, this is our speculative thread at this point. You already have the program. Why not just execute it speculatively? That's the idea. The processor in this Runahead mode speculatively pre-executes the instructions because you checkpointed the architectural state. You're not going to update that architectural state. You're not going to touch what's visible to the programmer. You're just going to run through the program, run ahead through the program, speculatively execute it without stalling as much as possible. So speculative pre-execute instructions, how do you not stall? Well, the purpose of this pre-execution is purely speculative to generate prefetches. And you don't stall because you don't wait for cache misses. Essentially, generate the cache miss, send it out to the memory system. That's essentially a prefetch, right? And then the program, okay, it doesn't wait for that value. It says basically, this value is not available, so I'm going to move on. I'm going to kick the instruction out of the window, basically, so that I can bring in more instructions into the processor. That's the idea over here. So this way, you can actually use a small window to process many, many instructions while the cache miss is going on, and you can generate these cache misses. So when the original miss that caused entry into the speculative pre-execution mode returns, you restore the checkpoint. Basically, you said, oh, I checkpointed the architectural state. I did some speculative pre-execution. I'm going to restore the checkpoint, program counter, as well as register file, so that I can restart as if nothing happened. Architecturally, nothing happened. From the programmer's perspective, nothing happened. Underneath, the processor prefetched lots of good stuff, hopefully, right? So it flushes the pipeline to be able to do that, and it resumes normal execution. Let me give you a picture of pictorially how this operates. So perfect caches, that's ideally what everyone wants, right? You never stall. Good luck. Not easy. What you get is small instruction windows. You get a long cache miss. You execute a little bit, and then eventually your window becomes full. Not much happens in the machine during that time. That's a stall. And that stall is actually long, as you can see in this picture. And then the miss comes back, the processor continues, computes until it gets to the next miss. And at the next miss, the same thing happens, basically, as you can see, right? This is why most of the time you see those red stalls dominating the execution time, right? This is what happens in real programs that are actually accessing data, not the toy programs that are fitting in the caches, let's say. Or not if you're very lucky, or if you're extremely smart that you ensure that everything fits in your cache whenever you do that. But extreme smartness has its limits also, because data set sizes are huge today. Okay, so what does Runahead do? Essentially, Runahead, when the processor gets to this long latency cache miss, after some point, it becomes the oldest instruction. Oldest instruction is nice because you can checkpoint the state nicely when the instruction becomes the oldest. At this point, the processor and hardware checkpoints the architectural state and enters a speculative processing mode. It keeps processing instructions, basically. It doesn't stall. And instructions that cannot be executed quickly for some reason, it could be a cache miss, it could have an exception, it could be a long latency floating point operation, etc. You mark them invalid and basically say, I don't need this data, I'm going to move on, basically. And essentially, the hope is that while you're executing this program speculatively instead of stalling, you get to this load 2 miss. You execute load 2 speculatively, and then start accessing memory. That's a prefetch, essentially. The second miss is a prefetch. And when the first miss returns back, this calls entry into the speculative execution mode, the hardware flushes the pipeline, saying that, oh, I'm done with run-ahead mode because I have the data that I needed to begin with. I'm going to flush the pipeline. I'm going to pay some penalty. That's the red part over here. And execute the load again, because I restored the checkpoint. And now I'm at program counter that caused entry into this run-ahead mode. So we execute the load. It hits in the cache because you just serviced it, right? And you compute. After some point, the second miss gets serviced. And when the main program and when the program actually reaches the second load now, non-speculatively, you get a cache hit. That sounds good. And you basically save a bunch of cycles. Now that's the beauty of memory level parallelism or prefetching, whatever you call it. You actually exploit both memory level parallelism and prefetching in this example, and speculative execution. Instead of waiting twiddling our thumbs and waiting, we actually worked hard, executed the program speculatively, and generated this second prefetch, or miss 2 over here, and overlapped its latency with the first miss, and also some computation over here, as you can see. As a result, we didn't need to expose the miss to the actual execution of the program. You overlapped its latency. Remember, out-of-order execution's benefit is latency tolerance. If you actually had a large window, you would get this benefit also. But the assumption is that we don't want these large windows, right? I'm going to get back to a retrospective about this also, because do we really want these large windows? Do we want more smart techniques like this? I would actually vote for this, frankly, because this is simpler, but of course, this has downsides also. Okay, so let me give you a little bit more. Instead of stalling during this long latency cache miss, generally, you pre-execute the loads and stores, and the ones that are independent of long latency cache misses generate very accurate data prefetches for both regular and irregular access patterns, essentially whatever the program is going to execute. And also there are other benefits. Instructions on the predicted program path are also prefetched into the instruction caches and outer cache levels, because you're really executing the program and prefetching everything that you need. And hardware prefetcher and branch predictor tables are also trained using future access information. It turns out this is beneficial as well. There's a lot of analysis that we did that shows that this looking into the future has benefits, essentially. Okay, but I can talk more about this clearly, but we don't have time. But let me give you the advantages and disadvantages of this. Clearly, with any idea, this has advantages and disadvantages. Advantages are very accurate prefetches. Essentially, the accuracy of prefetching is actually very high, more than 95% in many cases, for both data and instructions, because you follow the program path. In fact, it's nice because the program is already there and you're just executing the program speculatively. There's a disadvantage of this because you're executing the program, you're executing a lot of stuff that is not really going to be useful for prefetching as well, right? You can avoid that execution. Later works actually do that, which I will flash, but I'm not going to talk about. This is simple to implement. Most of the hardware is already built in. You just need to change it such that the control is different. There's no waste of hardware context, meaning you use the main thread, the context the main thread is executing for prefetching. Basically, you don't need to launch this on some other core or some other thread. IBM Power 6 is in a different way. They launched it on another thread, basically, so that they don't need to flush the pipeline of the main thread, actually. We want it to be more frugal, let's say. But the general idea is applicable, actually, to multi-thread machines, too. So there's no need to construct a special purpose pre-execution thread for prefetching. That's a big advantage because the software doesn't need to get modified, right? Of course, there are disadvantages and limitations. You may have already thought about it. Now you're executing extra instructions, right? So the trade-off is that you execute some more extra instructions and this reduces your execution time. Overall, this is a win in terms of energy, but because you're reducing the execution time also. But the downside is in some cases, it's not a win. Okay, so this is limited by branch prediction accuracy. This is why branch prediction and memory access are actually important. Whenever you're pre-executing threads, you'd better have a good branch predictor. Because you're pre-executing something, or get rid of the control flow instructions, of course, right? That's another option. But here we're executing the main program. We don't have the option to get rid of the control flow instructions unless you have additional hardware that you add. So you actually have a good branch predictor, you get much better benefits. Okay, you cannot prefetch dependent cache misses. You may have realized that, right? If a cache miss is dependent on the data that's prefetched, that's brought by another cache miss, earlier cache miss, like you're doing linked list traversals. Unfortunately, this doesn't work very well. So you need to be a bit smarter. We have some solutions, but I will not talk about those here. And the effectiveness is limited by available memory level parallelism. This means that you need to pre-execute so that you get to the next cache miss. Right? If the next cache miss is so far, this pre-execution can be completely useless. So later work's actually targeted to make sure that these disadvantages and limitations are minimized. Sunrock, for example, that did a lot of work in hardware to overcome some of these disadvantages, which we will not have time to get into. Prefetch distance, remember how far ahead you prefetch. We talked about this. Prefetch aggressiveness, let's say, is limited by memory latency because you actually stop this pre-execution when the memory returns the result of the first cache miss that caused entry into this mode, right? So it's good to think about that as well. Okay, so let me give you some results very quickly. These are actually Intel suites. We work together with Intel, and these are the production suites that they used to design their processors at the time. Nehalem processor, for example, or later Pentium 4s were designed using these suites. And on average, this buys you 22% performance improvement across many workloads on a strong prefetcher. So this is the importance of strong baselines when you actually evaluate things. If you actually evaluate this on a baseline without a prefetcher, you get even better performance improvements, as you can see. But with a prefetcher actually is able to capture some of the benefits of Runahead. So together, they're more synergistic in the end. Okay, so you actually get the benefit of large windows. I'm not going to talk about that in more detail. On an in-order processor, this actually improves performance even more. Because in-order processor, if you remember the in-order processors, don't have almost any latency tolerance, right? Of course, you can use prefetching in an in-order processor to get some latency tolerance, which is what this blue bar is. This is average, as you can see. So the red bar is about 40% over the blue bar, as you can see, on an in-order processor. So on an out-of-order processor, you get smaller benefits because out-of-order execution fundamentally is latency tolerant. So hopefully you're following this because this actually brings together many concepts in the course right now. Okay, now I like these two pictures because after we published this work, like 5 years later, after we showed these results, 5 years later, the chief architect of Sunrock processor put up the slide that shows essentially the same thing, which is interesting. These are different workloads, but they basically showed that, I showed you the slide earlier, right? They basically showed that on a similar processor configuration, what they implemented, they called it Scout. It's essentially Runahead execution. You get 40% better performance on these important transaction processing workloads that they designed their processor with at the same time, that they designed their processor for. Okay, there's more on Runahead execution, and I can talk a lot about this, as you can see, but I'll refer you to papers. I'm just going to, I'll also flash these papers because these are actually really interesting things that industry was writing at the time showing that they actually take ideas and they actually show benefits using these ideas in real products. Unfortunately, it's not happening as much today for various reasons. I wish industry went back and actually wrote papers about their processors and talked about what they've actually done. People are becoming a bit more conservative in exposing what they do, let's say. But these are actually interesting. You can see, for example, there's an analysis of Runahead execution versus conventional data prefetching in the IBM Power 6 microprocessor. And again, I'm going to skip these because we don't have time. NVIDIA has a very interesting version of this because they actually use dynamic binary translation, but you can read the paper if you're interested. Is there anything? I circled these because I like how they describe things. It's very similar to what we say. For example, this NVIDIA demo implements a Runahead feature that continues to execute microcode. They call it microcode because they actually execute from a microcode cache because they do dynamic binary translation in their system. Speculatively after a data cache miss, this execution can trigger additional cache misses that resolve in the shadow of the first miss. Once the data from the original miss returns, the results of the speculative execution are discarded and execution restarts with the bundle containing the original miss. We can read them more. I guess this is the interesting thing. These and some other features help Denver outperform Cortex-A15, which is the flagship ARM processor, by more than 2.6x on a memory read test, even when both use the same SoC framework, etc. You can read more. That's fascinating. So, okay, I don't have time to go over this, but if you are interested, you can read a lot more. Basically, this is an idea. Ideas are a dime a dozen. Making them work is the hard thing to do, basically. So what we did is after this idea, we said, okay, these ideas are a bunch of problems. Now let's make it work. How do you make it energy efficient? How do you make it more effective for applications where it doesn't provide a lot of benefits, like pointer intensive applications, linked list traversals, for example, tree traversals, graph traversals? And how do you actually make the branch mispredictions, let's say, behave? Or in the presence of branch mispredictions, how do you actually still take advantage of the idea? Another way of thinking about it. Again, you can find all of this information. It's in literature. In fact, I think NVIDIA uses some of these techniques because they reference this work in some of these papers that they have written. Okay, now let me give you some history a little bit because this is actually important. This also puts together multiple concepts. So we were doing this work in early 2000s. And at that time, there was a huge focus on increasing the instruction window. So basically people were saying, oh, we need to build large instruction windows. We need to build large instruction windows, which was interesting clearly, and designing bigger and more complicated machines. Eventually it happened. It took like 15 years or so, but it happened, let's say. Still, we're not very large, let's say. But Runahead was a different way of thinking. Basically, it said, forget about the large instruction window. Let's be simple. Let's keep the out-of-order core small and simple. Don't get rid of it, because getting rid of it actually brings you to in-order, which is not that good, let's say. No latency tolerance is not good. Let's keep it simple and small. At the expense of some benefits, let's take that hit, non-memory related benefits. But let's use aggressive automatic speculative execution solely for prefetching using the hardware infrastructure that we built. That's the idea. And this is one of the reasons why I want to instill this critical thinking in this course. And I keep emphasizing it, right? You should think critically. Hopefully, one of the benefits that you will get from this course is thinking critically. Because while people are thinking in one way, it's always good to think in some other way. And that other way actually may be very beneficial in the end. Because this could be synergistic with other methods that people develop as well, right? So a lot of interesting and innovative ideas ensued after this, but also there was prior work. I should also say that you should always know the prior work. This is an interesting prior work that proposed a very similar base idea on a very simple in-order processor, and we compare to it. You can find the paper. I also like this work that is an inspiration. This is the entire paper. It's one page, as you can see. You can read it here if you have very good eyes. Not me. But this paper basically says MLP, yes, ILP, no. What does that mean? Memory level parallelism, yes, ILP, instruction level parallelism, no. Basically, this paper is saying it's about the memory stupid. What it's saying is, let's deal with the big problem and let's not try to optimize the machine just for every single instruction. Focus on optimizing the machine for the big problem at hand, which is memory, and generate as many memory misses as possible. That's what this paper is saying, and it has a lot of ideas over here, some of which are still not explored as well, in my opinion. So if you're looking for research topics, this is a beautiful paper by Andy Glue. Okay, so let's see. I think I should probably use these slides in the last lecture, but I should also emphasize that we're going to talk in the next lecture about, let's say, fundamentally changing paradigms. But it's also important to look at the existing paradigms and think different ways. So this is clearly microarchitecture work, and it's critically important still today. So people have developed new microarchitectures that are larger windows, but this idea still has benefits. And also, I should mention that this was a great example of harmonious industry-academia collaboration. We actually collaborated a lot with Intel. And here I should show you the picture with the branches and loads. These are two fundamental problems that will not go away. Even if you change the paradigm, control flow and data flow will remain. Even when you go to data flow, control flow takes a different shape, right? It's decision-making, basically. These are decision structures. If you remember the data flow model of execution, the decision structure, the decision that you're making in a program will remain fundamental, and that will stall you, that will delay you if you don't handle it well. So these are the two major fundamental problems, and that's why we have advanced branch prediction and advanced prefetching lectures in this course. Okay, you can read the Test of Time Award. So this paper received one of the Test of Time Awards that was given by HPCA 18 years after its publication, but I like what they wrote. Okay, I should also say that even if the world is going a complete different way, you should think about going pretentious in some other way, because you can have an impact that way, right? So there was a lot of, for example, discussions that we had within Intel. A lot of people didn't believe that this would actually work, but we made it work, and we showed that it worked. So being resilient is important. And I think in the end, what is really important is data, right? Nobody can argue with the real data that if it's gathered correctly and accurately, right? If you can gather the data and show that, okay, this idea is good under these conditions, then you can make it work, right? That's what happened with Pentium MMX also, right? MMX extensions, right? I gave you a similar story at Intel in the 1995 or 1993, 1992, that time frame. Basically, people said, oh, MMX, will it work? Was it good? But eventually with data, with learning and scholarship, you can convince things. So quality of work over the work is also important. Okay, you can learn more about Runahead execution. I'm not going to talk about it. I also recommend more material on prefetching because I'm done with prefetching right now. But there's a lot of material out there because this is such an important topic. Any questions on prefetching? So at this point, I'm done. So we should take a break until 15 past, and then we're going to start virtual memory. Okay, let's get started with the second part of this lecture. Now we're going to switch gears, talk about virtual memory. We may get back to prefetching tomorrow very briefly for future directions, but I want to cover virtual memory, and you're going to see the more systems perspective of memory today. You will see virtual memory later on as well in some of the courses that you take. But I'll give you another assignment. This is building on the idea that we discussed on reinforcement learning. Essentially, this is an example of an intelligent architecture that makes decisions for itself, right? So this is an assignment where you read a short paper. It's a very short paper, actually, and you get 1% credit. Sounds like a deal? Of course, you need to evaluate it, right? Yeah. I mean, deadlines can be flexible, so we'll probably, I haven't thought about it much, but yeah. We should probably discuss the deadline, Mohammed. I don't know what we said for the other deadline also. Does that sound good? So 1% extra credit. Of course, do a good job. Don't just copy and paste the abstract of the paper. Doesn't work, for example, right? If you copy and paste the abstract, you didn't really evaluate the paper or review the paper. Anyone can do that. I guess you can ask ChatGPT to review the paper for you, and I'm curious what you get. But yeah. Okay, and that's the paper basically. That paper argues for this data-centric, data-driven, and data-aware paradigm for better architectures. Okay, so let's jump into virtual memory. You may talk about that more tomorrow, but we're going to talk about virtual memory. Here, I didn't add many readings over here, as you can see, except this is covered somewhat. Well, it's covered actually in not a bad way in H&H. I'm going to borrow some slides, so you can actually find some reading in your book because it's such a fundamental concept. Even though books ignore some of the fundamental concepts, like prefetching, they don't ignore virtual memory, as you can see. Okay, so the programmer's view of memory looks like this, essentially, right? Memory looks like something for you, and if you didn't take this course, memory would always look like this for you, basically. It's just some magic underneath. In fact, if you don't take any course that shows how a processor works, it's all magic, right? I cannot imagine a word like that, right? You write this program and some magic executes it, and you're not curious about that magic underneath. That's the reason why you have this course in a computer science degree, right? You're going to become a computer scientist or a computer engineer. Hopefully, this should not be magic to someone who claims to be a computer scientist, right? Maybe there should be better degrees or some other degree for people who want to keep it as magic, right? So that's the whole point of understanding how a computer works. So this is not magic, as you know, but from the programmer's perspective, we do loads and stores to memory, right? So we know that ideal memory underneath is not magic. Ideally, we want this magic also. We want zero access time, infinite capacity, zero cost, infinite bandwidth, zero energy, ... Today, we're going to tackle the infinite capacity problem a little bit. But we're also going to introduce other stuff because virtual memory is actually serving multiple purposes in today's systems. One is hiding the management of memory, hiding the capacity issues with memory from the programmer. And the other is protection, access protection, isolation, right? These are two completely different problems that are actually solved in an integrated manner in the virtual memory system. Okay, so remember the slide. We said we have virtual memory and programmer sees virtual memory, and this is an abstraction actually, because underneath there's some physical memory. And programmer can assume the memory is infinite, large enough. In reality, physical memory size is much smaller than what the programmer assumes. And things work. You write programs with large virtual addresses. In reality, that large of an address doesn't exist. You have a 64-bit address. We don't have 2 to the 64-byte memories, right? If you have that, please let me know. I'd like to use it. So basically, physical memory size is much smaller than what the programmer assumes. And underneath, there's some magic. The system, using some magic, meaning using software and hardware cooperatively, maps virtual addresses to physical addresses, virtual memory addresses to physical memory. And we're going to uncover that magic today. The system automatically manages the physical memory space transparently to the programmer. And this is another reason why this was a very successful idea. If you actually had to find system ideas that have been extremely successful, virtual memory is one of them. But hopefully we'll also say that this may not be the best way to go forward by doing critical thinking either later today or tomorrow. Okay, but it's been very useful. So programmer, essentially the big benefit is programmer does not need to know the physical size of the memory, nor do they need to manage it. A small physical memory can appear as a huge one to the programmer, and essentially life is easier for the programmer, right? And we're going to actually add more and more over here. This is a simplification because there are other benefits of virtual memory, as we will see. But of course, the downside is somebody needs to pay the cost of actually making this work, and that's the system software and architecture, essentially, microarchitect and the system designer. And this is a classic example of the programmer microarchitect trade-off, right? You make programmers' life easy by making microarchitects' life hard. Precise exception is another example, right? We retire instructions in order, and we have to pay the cost of doing so. So this requires, virtual memory requires indirection and mapping between virtual and physical address spaces. And this will become more clear because you need to, programmer sees a virtual address space and then there's a physical address space, and there needs to be some translation that needs to happen from the virtual space to the physical space and mapping that happens, because not the entire virtual memory that the programmer sees is going to be in the physical space. Okay, so let's talk about benefits of this automatic management of memory. Basically, we're talking about automatic management of memory. Programmer doesn't need to deal with physical addresses, and this has a lot of benefits, actually. Each process has its own virtual address space, which is very large. Basically, for practical purposes, infinite. You can run out of virtual memory space also, but maybe you're not doing something right if you're running out of virtual memory space in your memory management. Maybe you have a memory leak somewhere, right? Possible. Each process is an independent mapping of virtual to physical addresses. Basically, this is very important to know. Each process or each program has a different view of virtual memory. Independent, completely independent. They may share parts of the physical memory through the mapping, their own mappings, but they are independent on the virtual memory address space. On the other hand, threads within a process share the virtual memory space. That's the difference between process and thread, right? Which you will also see, I think, when you take systems programming. So virtual memory or this automatic management of memory enables multiple things. It enables code and data to be located anywhere in physical memory because you have this indirection, right? This will become a little more clear. Basically, you can have relocation and flexible location of data and code. If the programmer directly encoded a physical address, and that physical address, basically, the code has to be there, right? Whereas if it was a virtual address and there's a translation mechanism afterwards, the system can load the program into any location in physical memory by just changing the translation, right? This gives a lot of flexibility to the system. I mean, hopefully it's obvious, but you will see more. This also enables the isolation or separation of code and data from different processes in physical memory. So if somebody writes a program X and you write program Y, these can be isolated from each other because the system has actually different mappings, virtual to physical mappings. This is called protection and isolation, and we will see that essentially. So I should also mention that this is important because this is what enables multi-programming. Multiple programs can be present in the same machine. Otherwise, they're very, if you don't have some sort of translation or indirection, it's very difficult to enable because I write a program and I want it to be executed, and I assume some physical addresses. Somebody else writes a program, they assume some physical addresses. What if those physical addresses overlap? How are these two things going to execute if there was no translation mechanism, right? It's not going to happen clearly because they will, I do a write to a physical address A, somebody else does a write to a physical address A. Clearly, these are different programs. They should not be writing to the same location because that address A means something else for each of the programs, right? These are semantically completely independent. But if you don't have a mechanism of remapping those addresses somewhere else, meaning if the programmer directly gets exposed to the physical address on the machine, you will have that problem. You cannot execute multiple processes at the same time. Okay, and then the other benefit of this is code and data sharing between multiple processes also happen through virtual memory. So you may, again, I write program X, somebody else writes program Y, and we want to share data somehow with each other. What do? I call my friend and say, oh, I'm writing this data value to physical memory location A. So you'd better read from physical location A. That's what you do today, right? No, you don't do that today, right? So basically, you use some shared memory constructs today, or shared libraries, right? If you have shared libraries in a machine, how the different programs can call functions that are shared. Okay, these will become more clear, but essentially these are enabled by automatic management of memory. So a system with physical memory only, essentially, CPU generates physical addresses, and this is really the physical memory. load or store instructions generate physical memory addresses. Early computers were like this. Today, this is not the case. Although you could make x86, for example, work in physical mode. It's called real mode in x86. So if you want, you can actually make this work. So this sort of thing is visible to the BIOS, for example, the system, a very low-level system software that enables the big startup of your machine, because you have to access physical memory directly so that you can load some things like page tables, as we will see. But today, most programmers do not directly manipulate physical addresses. Okay, so basically, in a system that looks like this, let's assume that this is the baseline, physical memory is of limited size because of cost reasons. We've seen that, right? What if you need more? Should the programmer be concerned about the size of the code and data blocks fitting physical memory, right? You write some code, your code is larger than the physical memory. What do? Do you actually do the hard work to manage the data movement from disk to physical memory? Well, if you start doing that, it becomes very difficult to program this machine. So we're going to tackle this problem with virtual memory. Multiple programs may need the physical memory. Should the programmer make sure all processes, different programs, can fit in physical memory? We just said that it's not possible because different people may be writing different programs. And even if the same person is writing, it's a mess to actually think about this, right? Should the programmer ensure that two processes do not unintentionally or incorrectly use the same physical memory portion? This was the example that I gave you earlier, writing to location A by two different programs. And then there's another problem, which is actually interesting because your instruction set architecture may be forward-looking. They may have an address space greater than the physical memory size, right? Today we have 64-bit addresses, right? 64-bit address space with byte addressability is 16 exabytes. How many of you have 16 exabyte memory? Not even supercomputers have 16 exabyte memory today, unfortunately. So clearly we have an address space that's much larger today. So how do you actually deal with that, right? I mean, this is actually interesting because this is actually, the address space is virtual. That's why it's 64 bits, but keep with the problem for now. Okay, so basically, what if you do not have enough physical memory? Then you still need to have this mapping mechanism that we're going to talk about. So the difficulties of direct physical addressing is a lot. Essentially, the programmer needs to manage the physical memory space. This is inconvenient and difficult, clearly. It used to be this way. People used to manage their physical memory actually in the 1950s, 60s. Good that you're not in those times, let's say. It's more difficult when you have multiple processes. It's difficult to support code and data relocation because addresses are directly specified in the program, right? You cannot relocate the data easily, or you cannot relocate the data essentially if you don't have some indirection or change of address. It's difficult to support multiple processes, especially concurrently, because you need protection and isolation between multiple different processes. And sharing of physical memory space without problems becomes not easy to handle. And finally, difficult to support actual data and code sharing across processes because different processes need to reference the same physical address. And we talked about that also, right? How do you actually communicate that you are supposed to reference this particular address? So essentially, virtual memory solves all of these problems with a single idea, let's say. And the idea is very simple. Give each program the illusion of a large address space while having a small physical memory. Okay, so that's a very high-level idea, clearly. The question is, how do you do that? We're going to talk about that. But the programmer does not worry about managing physical memory within a process or across processes, essentially. Programmer can assume they have infinite amount of physical memory. Hardware and the software cooperatively and automatically manage the physical memory to provide the illusion that we want. And illusion is maintained for each independent process. I have to emphasize this. Virtual memory is not a system-level thing, it's a process-level thing. Each process is its own virtual memory. Okay, so let's talk about the basic mechanism. Basic mechanism is very simple, indirection and mapping of addresses. Essentially, address generated by each instruction in a program is a virtual address. It's not directly specifying anything, any physical entity, basically. It's a virtual address. It could be, you can think of it as a name, right? It's a namespace. It's a virtual namespace. It's definitely not the physical address used to address main memory. It's going to be translated to the physical address that's going to be used to access main memory. This is also called a linear address in x86. x86 has interesting terms. This is where I don't think they did a good job in terminology, let's say. And then there's an address translation mechanism maps this address to a physical address. And we're going to talk about that address translation mechanism. That physical address is called real address in x86, which is not bad actually, in terms of terminology, let's say. And the address translation mechanism can be implemented in hardware and software together. I'm giving you the x86 equivalents because I'm going to show you some examples from x86 here. Okay, so let me give you the conceptual view. This is from the book chapter that I assigned to you. I like this high-level view. Essentially, you have illusion of large, separate address space per process. This is essentially summarizing what the mapping and indirection looks like. In this case, you have two processes. They have independent virtual address spaces. And you can see that each of them have a view of virtual memory that's 256 terabytes. That's 2 to the 48, right? Bytes, essentially 48-bit byte addressable address. The other process also has a virtual address space. But then there's a physical address space. This is actual physical memory. And this system, this processor may have 8 gigabytes of physical memory, right? So essentially, the programs have the illusion that they are operating on 256 terabyte address space each, but individual portions of or chunks of the virtual address space get mapped to physical memory at a given point in time. So essentially, the physical virtual address space is divided into virtual pages. We're going to talk more about that. In this case, 4 kilobyte virtual cases. That's an example. It could be 1 megabyte, 1 gigabyte. We will see. But 4 kilobyte portions of the virtual address space actually get mapped to the physical address space, and they're present in the physical memory at that point in time. So there needs to be a table that records this mapping clearly, right? What is for this process, for process 1, where does virtual page 0 in this particular case get mapped to, right? Does it get mapped to physical page 0? No. It gets mapped to physical page, whatever, but it's actually 0, 1, 2 in this case, right? As you can see. On the other hand, the virtual page 0 of this process gets mapped to physical page 0. So somebody needs to manage this clearly, okay? So that's what the indirection mapping means. You have a virtual address in your program. By some indirection mechanism, you indirectly access physical address space, and that indirection is enabled by mapping of the virtual page number to the physical page number through some lookup table that we will call the page table, okay? So let's take a look at that page table. Essentially, we need to translate the address. Essentially, let me go back here. As opposed to this picture, well, wow, it was so far away. Even more. Okay, as opposed to this picture where you're directly generating physical addresses, we have an indirection. Okay, essentially the indirection is this page table, right? The CPU program generates virtual addresses, and you consult this lookup table called page table, and the page table basically says, oh, this virtual page for this process is in this physical page in physical memory. And if you access something that's not in physical memory, it says, oh, it's in disk somewhere. So I'm going to call the system. I'm going to ask for help. This is called an exception. Remember the exceptions and interrupts vector? This is called a page fault exception. The page that the program is referencing is not in physical memory. So I'm going to ask the operating system to help me bring it to the physical memory. And we're going to talk about how that's done. The I/O controller needs to get into the process and handle the exception. Essentially, a page needs to be moved from the disk to the physical memory. And then the mapping needs to be fixed such that that page, the page table entry of that page points to the physical memory page where the page is put into from the disk. Makes sense, right? So this is all done automatically. If it was not done automatically, the programmer had to do all of this. And there was a time in the world 50, 60 years ago when that was the case, okay? In some systems, actually, but in maybe 20 and 10 years ago, right? In some cases, maybe it still exists, but very small amount. So basically, the hardware converts virtual addresses into physical addresses via this lookup table, page table. But this page table is actually cooperatively managed by the operating system and the hardware together. So we're going to talk about this management. But this makes sense, right? You have virtual memory address space. Some pages in that virtual memory address space is in the physical memory. These are these indirections or these mappings. Some pages, because they have not been accessed recently, for example, are actually on the disk. But you have a mechanism to bring it from the disk to the physical memory. This way, this is why disk is a backing store of virtual memory, of physical memory. And this is why physical memory is a cache of the disk from this perspective, right? From the program's perspective. So essentially, all of the caching principles apply to physical memory as well, as we will see. In fact, I'm going to show you a slide where caching terminology and virtual memory terminology are going to be very similar. Okay, so let's take a look at these two different processes. Each process has 4 GB over here. I'll go through this relatively quickly. Basically, sizes don't matter in this case. This is a small system, as you can see. Physical memory is small. We divide the virtual memory of each process to virtual pages and divide the physical memory into physical pages. I will also call physical frames. You may actually see both, but we'll use physical page in general. And then there's a mapping of the virtual pages of process 1 to the physical pages in physical memory, and ditto for process 2. And that mapping is done through the page table. Clearly, there are many issues in this injection and mapping, right? When to map a virtual address to a physical address. Let's answer that actually quickly. Essentially, when the virtual address is first referenced by the program, nothing has to be in physical memory. Well, the code hopefully is that you're executing, but even the code, right? You have a program counter. The program counter is virtual address. You go through this translation mechanism and get a page fault, and the code gets brought from the disk into the physical memory after that page fault. And then you can reference that program counter in physical memory, right? So basically, whenever you touch a virtual address the first time, that virtual address gets mapped to a physical address through the page table. Of course, you can do prefetching on this as well, right? So you can actually pre-populate this page table, both from the operating system perspective and hardware perspective. So what is the mapping granularity? This is important. I showed you 4 kilobyte, for example, right? But it could be byte granularity. It could be kilobyte. It could be megabyte. It could be gigabyte. We have multiple granularities. Existing systems actually have multiple granularities with some pain. This is not an easy task, let's say. But this granularity determines the size of the tag store, which is a page table. Page table is actually a big tag store, if you think about it, right? Because physical memory is a cache for the disk. Essentially, if you have byte granularity, that mapping is very small, right? And you don't want that because the tag store is huge. And also, you're not exploiting locality very well if you have pages that are of a size of bytes. If it's 4 kilobytes, not bad. 16 kilobytes, 64 kilobytes, they exist. Megabytes, gigabytes, now we're going to talk about these. Basically, similar issues like caching over here, right? This is, you can think of it as a cache block size, similar to page size. So where do you store and how do you store the virtual to physical mappings? We're going to concern ourselves with this a little bit. Basically, this has to be an operating system visible data structure. Do you also cache it in hardware? We're going to see the answer is yes. Do you manage it cooperatively? And we're going to see the answer is yes. So this is actually a very great example of hardware-software cooperation also. All of the systems actually do this today. So when do you do, what do you do when the physical address space is full, when your physical memory is full? Well, remember, physical memory is a cache, right? Essentially evict an unlikely to be needed virtual page from physical memory and fix the mappings in the page table. That's the idea, because page table is a tag store, right? Okay, so basically, if you think about physical memory as a cache and the backing store as the next level, and the page table as a tag store, all of this becomes easy, in my opinion, because we've already seen caches. Okay, so virtual, let's go into a little bit more detail. Virtual address space is divided into pages. Physical address space is divided into frames, just to be a little bit different, because it's actually a physical location, frame of a page, if you will. But people call it pages also. That's why I have this IE pages for now. But let's stay with the frame terminology for some time. A virtual page is mapped to a physical frame if the page is in physical memory. Okay, that's what the mapping specifies in the page table for that virtual page. Otherwise, the virtual page is mapped to a location in disk, assuming it's allocated. There's also the memory allocation part that we're not going to discuss as much. I'm going to assume all of memory is allocated, but actually when you program, you allocate some memory, and that allocation enables you to have a mapping to the disk or physical memory. But for now, ignore that allocation, let's say. Otherwise, it will complicate things, but there's another level of allocation over here, which is different from what we're talking about here. Assume all of the memory is allocated, all of the virtual address space is allocated, then a virtual page is mapped to a location in disk or a physical frame. If you access a virtual page and it's not in memory, but it's on disk, virtual memory system brings the page into a physical frame and adjusts the mapping. This is called demand paging. And the fact that you found the virtual page not in memory is called a page fault. And we're going to see that. And page table is a table that stores a mapping of virtual pages to physical frames. And you've seen an example, we're going to see more. So in other words, basically physical memory is a cache of the cache for pages that are stored on disk. In fact, it's a fully associative cache in modern systems. A virtual page can be mapped to any physical frame. Okay. Similar caching issues exist as we have covered earlier. Placement, replacement, granularity of management, write policy. And we're going to see some of these again, but we're not going to talk about a lot of these. So for example, where and how to place and find a page in cache. What page do you remove to make room in the cache, meaning physical memory? Do you have large, small, or uniform size pages? What do we do about writes? When you write to a physical page, do you also write to a copy on disk? And people quickly figured out that it's a very bad idea to have write through physical memories. So today, our physical memories are write back, meaning you have a modified bit in the page table. This is the same as the dirty bit or modified bit that we've seen in the caches. For a given virtual page, you have a modified bit. If the program has written to that page, that modified bit is set. And when you have to evict that page from physical memory to make room for some other page coming from the disk, you have to write back that page that is marked dirty into the disk. Makes sense, right? But this is not news for you because we've already covered caching. We just changed where the cache is, essentially. Okay, so this is essentially analog. A cache block is analogous to virtual memory page. Cache block size analogous to page size. Block offset is a page offset. A cache miss is essentially a page fault in this case. The index into the cache is the virtual page number in this case. The tag store or metadata store is the page table, and the data store is actually the physical memory. Physical memory is your data store right now. Okay, I like the slide, as you can see. It simplifies a lot of the concepts. But let's go into virtual memory a little bit more. So page size is the mapping granularity of virtual to physical address spaces. It also dictates the amount of data transferred from hard disk to DRAM at once. And the reason a lot of the page sizes today are 4 kilobytes are historical because the disks were designed that way. They could bring, let's say, 512 bytes, 4 kilobytes easily through streaming. We actually still have this legacy of disk-based virtual memory systems. That's why you see 4 kilobyte pages today in many systems. It's unfortunate, but that's how it is. Basically, we're assuming that you're transferring all of that amount, 4 kilobytes, from the hard disk to DRAM to put a page into the physical memory. Hopefully that makes sense. But again, we've seen in caching, sub-blocking or sectoring, right? You could actually play similar tricks in virtual memory. Of course, you need to be a little bit more careful because now you need to change the page table. Because remember, sub-blocking or sectoring enabled us to bring only a piece of the cache block into the cache. You could do that in physical memory as well, but it requires you to actually have the valid and dirty bits separately for different sub-pages in this particular case. Okay, page table is the table that stores virtual to physical page mappings. It's essentially a lookup table. Basically, it's used to translate virtual page addresses to physical frame addresses and find where the associated data is, essentially. An address translation is the process of determining the physical address from the virtual address. So hopefully these are clear. Now let's take a look at how this is done. I've already shown you this picture. Now we're going to actually see some examples. Essentially, this picture is from your book. You can see the chapter. The hope is that most accesses sit in physical memory. So essentially, these are your virtual addresses. There's an address translation mechanism. Some of your virtual addresses in physical memory. Some of them are in hard drive or SSD, essentially disk. The hope is that most accesses sit in physical memory, but programs see the large capacity of virtual memory such that the programmer doesn't need to worry about the sizes of data or code. This is essentially the idea of a memory hierarchy also, right? If you think about it, this is what we said, right? Most accesses we want, it should hit in the fast memory, and we should get the capacity of the large memory, right? That's the idea. So you can think of this as, this is the cache, and this is the large memory over here. Okay, so this is what address translation looks like. You take a virtual address, in this case, it's 32 bits. You chop off the bottom bits like page offset, because that's the page size. Those bottom bits don't change during the translation, but the top part, the page number, virtual page number, gets translated to a physical page number or physical frame number. Let's call it physical frame page number. That's what your book uses. Makes sense, right? By just looking at this, now you can tell what's the size of your physical memory, right? It has 27 bits, so it's 2 to the 27 bytes, assuming it's byte addressable. And your virtual address is 32 bits, is 2 to the 32 bytes. Makes sense. So this translation mechanism we're going to look at. So essentially, a 19-bit virtual page number gets translated to a 15-bit physical frame number. Everything is good, right? So let's take a look at the example. Actually, this was 31, sorry. Yeah. Virtual memory size is 3 gigabytes in this example. So I have 3 to 31 bytes. Physical memory size 2 to the 27. Page size is 2 to the 12, 4 kilobytes. Essentially, the organization looks like this. Virtual address is 31 bits, physical address is 27 bits, page offset is 12 bits. So the number of virtual pages you have is 2 to the 19, number of physical pages 2 to the 15. So you can actually easily drive the virtual page number and physical page number. These are easy. And this is an example from your book also. This is what your virtual memory looks like. This is what your physical memory looks like. The blue items over here, or the blue pages, actually are present in physical memory. And we're looking at the granularity of virtual pages and physical pages, as you can see, right? This, for example, shows that virtual page 2 is mapped to physical page 7 FFF. And clearly, physical memory is smaller. Okay, so essentially, how do we translate addresses? Page table has entry for each virtual page. So for every possible virtual page number, you need to have an entry. And each page table entry has a valid bit. This valid bit says if the virtual page is located in physical memory. Basically, if it's 1, the virtual page is actually located in physical memory. Otherwise, it's somewhere else. So you need to have a mechanism for finding where it is. This stuff can be stored in the page table or some other data structures in the operating system, which we're not going to get into. But it must be fetched from the hard disk somehow. I should actually call it a backing store because it can be something else. Right? It could be tape. It could be some SSD. Physical page number is where the virtual page is located in physical memory, assuming valid bit is 1, right? And then there are also some other bits in the page table entry, like dirty, modified, we talked about, replacement policy bits. What are you going to replace? How similar to the cache replacement, basically. We're going to look at that also. And then also permission and access bits. Can you access this page, given that you have some privilege level in this process? We're going to talk about that because this is separate from address translation. Essentially, it enables virtual memory protection. Okay, so ignore those permission access bits for now. So let's take a look at this example page table for the example in your book. Essentially, you have virtual page numbers, and this is your page table, ignoring the access protection and other replacement policy bits. You have a valid bit that's set for only those virtual pages that are in physical memory, and it shows the mapping, as you can see, right? So in this case, you see 1, 2, 3, 4 of the virtual pages present in physical memory. Okay, let's take a look at the address translation, how it's done. Basically, you take the virtual address, 31 bits, chop off the page offset, because this doesn't change during translation, because that's the page size. You find the virtual page number. You use the virtual page number to index into the page table. Remember, page table is also something in memory. So now you need to think a little bit. Basically, you need to index into the page table to get the page table entry. And that page table entry specifies the valid bit and the physical page number. Right? So basically, page table is located at physical memory address specified by the page table base register. Now here, you need to think a little bit because in order to access memory at a virtual address, you need to access memory to get to the page table entry first. This is the indirection, right? This is why the load indirect is a nice instruction in LC3, for example, right? But basically, we're assuming that the page table is an entire memory. We're going to deconstruct that soon because how are you going to have this huge thing in physical memory, right? But basically, there's a page table base register. It's a physical address. You add to it the virtual address times the page table entry size, and that gives you the address of the page table entry that you're looking for to do the translation, okay? Basically, page table is indexed with the VPN, virtual page number. The page table provides the PPN, which is the physical page number, which is, in this case, 0x7FFF, and it's valid. So the translation is basically concatenating the page offsets with the physical page number. Right? So page offset bits don't change during translation, as expected. Makes sense, right? Okay, so we're going to look at a bunch of issues over here, but let's go through a relatively simple example. What is the physical address of virtual address 5F20? We first need to find the page table entry containing the translation for the corresponding virtual page number. So what is the virtual page number? You need to figure that out. We're going to figure that out soon. And then we look up the page table entry at the address. meaning do a memory access there. And what is the memory access that you need to do? Essentially, there's a page table base register. We add to it the virtual page number times the page table entry size, because each page table entry occupies some amount of space, right? So let's do this for the question that I asked earlier. 5F20, if you look at it as a 31-bit entity, you'll figure out that page offset is F20 and virtual page number is 5. So VPN is 5. Meaning entry 5 in page table indicates VPN 5 is in physical page 1. Well, we basically look up the page table in entry 5. This is entry 0, 1, 2, 3, 4, 5. It's valid, meaning it's in physical memory, and the physical page number is this. And we do the translation, so the physical address is 1F20. Makes sense. And then the question is, another question, what is the physical address of virtual address 73E0? We do the same thing. VPN happens to be 7 over here, because the bottom 12 bits are the page offset. We look at the entry 7 in the page table, val bit is 0, which means that this virtual page is not in physical memory. That means that whatever I see over here is not useful for me for translation, but it may be useful for figuring out where this is. So this is a page fault exception. At this point, exception handling happens. Remember precise exceptions lecture when we talked about exception handling? This process, you save the architectural state, and then you basically give an exception code, and an exception handler is called. This exception handler comes in, it checks what's going on. It says, oh, this is a page fault exception, so I better service this page fault. So you jump to a page fault exception handler that services that page fault. We're going to see that soon. Okay, so let's take a look at some of the issues over here. So page table size, we should tackle this because this is going to be hairy if we don't tackle it. So let's take a look at a bigger virtual memory address space like we have today, 64 bits, right? So if you look at this, assuming 4 kilobyte pages, page offset is 12 bits, virtual page number is 52 bits. Assume that your physical address space is 40 bits. Your page table is responsible for translating 52-bit virtual page numbers to 28-bit physical frame numbers or physical page numbers. Sounds good. Okay, I can deal with it. But how large is this page table, really? Well, 52 bits means 2 to the 52 entries, right? First of all, that's to begin with, it is a large number. Assume conservatively that it's only 4 bytes per entry. In existing page tables, actually, it's larger. So this is 2 to the 54 bytes. That's 16 petabytes, right? Do you have it in your physical memory? I wish I had it. I wouldn't use it on page tables if I had it. Let me put it that way. Basically, and that's just for one process. Never forget that. If you're running 100 processes, multiply this by 100. If you want 1,000 processes, multiply it by 1,000, right? Basically, this is not realistic. And the process may not be using the entire virtual memory space. Allocated, not allocated comes into play, but I'm not going to talk about that over here. Basically, this is not realistic today. So a page table is large. It's actually huge. But at least part of it has to be located in physical memory. We said that page table base registers in physical memory, right? So how do we get rid of locating entire page table in physical memory? Clearly, we're not going to be able to do that. So solution is more indirection. Essentially, multi-level or hierarchical page tables. In other words, this is more indirection. We'll see that we'll do more indirection. We're not going to get to the page table entry immediately. We're going to go to another level of page table that gives us the page table entry. Okay, so multi-level page tables. Basically organize the page table in a hierarchical manner such that only a small first level page table has to be in physical memory. And that small first level page table hopefully is 4 kilobytes or 8 kilobytes, right? So that's the idea. Essentially, this is from your book. This is what it looks like. You have, you chop the address into 3 things. The top part specifies which page table to look up. So this is called the page table number. And then there's an offset inside that page table. So essentially, this is the first level page table. You can see that it's 9 bits, right? So you index using this first level page table. This gives you the base register of the page table that you actually need to index. Makes sense, right? In a 2 level, after one access to the first level, you get the base register of the page table you actually need to index that houses your page table entry that you're looking for the translation in, right? So, okay, let's take a look. Page table number, you index here. Of course, this needs to be in physical memory now, but this is small. This is 2 to the 9 times 4 bytes, let's say. or 8 bytes, whatever, right? Basically, it's smaller than 4 kilobytes or equal to 4 kilobytes. So it fits in your page also nicely, right? So the entire virtual memory system is designed based on this principle. The first level fits in your physical page, and it stays in physical memory so that you don't get a page fault on your page table, right? First level page table. But on the other level page tables, you can actually get a page fault, which is actually interesting. Okay, so let's not get ahead of ourselves. Essentially, this is the page table address, and that gives you which page table you're going to index. And this is your index into that page table. So each of these page table is 1K entries, as you can see, but you have many of these page tables. You can calculate how many you have. I'm not going to do that right now. So first level page table must be in physical memory. Only the needed second level page tables can be kept in physical memory. So if you haven't touched that memory, you don't need to bring the page tables that do the translation for that virtual memory address space. So this is another beauty of multi-level page tables. It solves the problem of not having or problem of having having your physical memory covered with the page table, right? Only the page tables that you have touched are brought into the physical memory. Okay, so this is an example, as you can see. This is the address that we have. This is the page table number. And this is 0. Essentially, we're accessing, we want to find the page table address for page table number 0 over here, the top 9 bits. And that's the page table base register, which happens to be in physical memory in this particular case, right? Essentially, essentially it is in physical memory, sorry, it's valid, as you can see over here. And then you can access it, yes. And then the translation is also there. Basically, the page itself is in physical memory. So here, the top level page table, the page table that you're looking for is in physical memory. And then the page you're looking for is also in physical memory. But if you actually access page table number 01, you can see that it's not in physical memory, right? The page table that you're looking for is not in physical memory. So that's a page fault for the page table you're looking for. So the virtual memory system needs to bring the page table you're looking for into the physical memory and fix the mapping over here. Okay? I know there's a lot of injection going on, but you'll get used to it. So basically, we solved some problems with more indirection, but this cost us something. For n-level page table, now we need n page table accesses to find the page table entry, assuming all of those page tables that we're looking for are in physical memory. So n accesses, we were just doing one additional access. Now we want n accesses. This is going to increase our latency to actually get the translation. So let me give you an example from x86 architecture. You can see that x86 nicely called this page directory. So CR3 is the physical address. So basically control register 3, or this is the page directory base register. You add to it the top n bits from the directory entry, and then this gives you the base register of the actual page table. And then you index that page table using the part of the linear address. That gives you the PTE, and then PTE concatenated with the offset is the physical address, essentially. So with small pages, that's what it looks like. This is 10, this is 10, as you can see, 10 bits, 10 bits. And you can see everything fits nicely in 4 kilobyte pages if you do that. But x86 actually has large pages also. This is a 4 megabyte page. Large pages are single level, as you can see, right? So you have a single level page table. x86 also has large addresses. This is 48-bit address, and they have 4-level paging. Because I don't remember what PML4E means, I had to write it, page map level 4 entry over here. Basically, you take the page table base register, index into it using this top 9 bits. That gives you an address that will start the next page table and index into it using the next 9 bits. And then that gives you another address that will start with the page directory. That's the start of the page directory. You index into it using these 9 bits. And finally, you get your page table base register from there and index into it using this address 9 bits over here. And you get the page table entry, hopefully. And assuming these are all valid, 1, 1, 1, 1, 1, you'll get the physical address after 4 translations. But you can also get 4 page faults over here, right? So basically, your latency can be very high if you get 4 page faults. Okay, I think this is a great place to stop because we're going to move to the next challenge. And next challenge is going to introduce more caching, let's say. So we'll pick up here tomorrow and finish up virtual memory and talk about some